My name is Kirill Bogdanov. I'm a principal solutions architect at AWS. I work with global financial services, primarily in the area of high-performance computing. And with me today, Flamur Gogolli.
Hello, everyone. My name is Flamur. I think I've spoken to quite a few of you already the last 2 days. I work for AWS as well. Together with Kirill, we are two of the core maintainers of a product called HPC Grid, and we're here to talk to you about that today.
All right. So before we're going to dive into details, Before we're going to dive into details, I would like to give you just some key points that I would like you to take away from this presentation. When it comes to high-performance computing grids, there are a number of reasons, including market volatility, regulatory requirements, and aging hardware that pose challenges for running the systems on-prem in an efficient manner. And these are the reasons why financial institutions looking for the alternatives and they migrating their workload into the cloud. Now, at the same time, many of them take the opportunity to modernize their workloads. And to help financial institutions on the spot, we have built HPC Grid, which is a reusable blueprint that provides a reference architecture for modern container-based solutions. It uses common cloud services and addresses the problems above. Now, HPC Grid is the result of multiple engagements, multiple prototyping engagements we had with our customers, and it incorporates our experience and best practices. Now, today, there are several major European banks that use HPC Grid in production. So basically, the grids that are built on top of the architecture are used in production. So therefore, this architecture is quite well tested and quite well performed. Now, this year, we have donated HPC Grid to Finos with our main objective just to get collaboration from the broader community and to build a cloud-agnostic open source solution. Now, just to bring everyone on the same page, I would like to give you an example of where compute grids are used today. Now, this is an example of a FSI risk pipeline. So while the actual implementation might be different in different FSIs, but the overall concept are quite the same. Now, as the data travels from left to right, we have different triggers that, for example, the market closure or the trades that instantiate different events generations, right? So different scenarios that needs to be evaluated. Now, in the next stage, they merge with the appropriate data that comes from the market, from the trades. All this has been prepackaged for the processing and then it's been sent for high-performance compute grids. Now, this is the part in the middle. Now, compute grids in the modern banks, they comprise from anywhere from thousands of CPUs to hundreds of thousands of vCPUs, and often they are distributed across multiple data centers for high availability and disaster recovery. And therefore, you can imagine they are quite complicated pieces of infrastructure to maintain, and they are very expensive as well. And at the same time, they exist in the critical part of the daily operations of the bank. And therefore, financial institutions looking for the ways to reduce their risk of running the systems and at the same time reduce the cost where possible. Now, I'm not going to talk about the post-processing of the data. It's not so much related to this context, but in the context of the presentation, the HPC Grid, that will be a component that will be equivalent to the high-performance computing grid located here in the middle of this architecture. Couple of other interesting things. So if you look at the utilization of high-performance compute grid in the on-prem, we can see a clear diurnal patterns. So there are different types of the workloads. Some of them run overnight, like overnight batches, and some of those workloads run during the day. And overnight, what we usually see is that utilization of the grid is maximized, and while at the same time during the day, the utilization is underutilized, right? Which creates the obvious demand from the customers to, first of all, to be able to run more workloads faster, but at the same time, don't increase the cost when you have underutilized workload. There's also one very peculiar aspect about FSI workloads. And here on this graph, you can see a distribution of the task durations that has been sampled from the production workload. This is a result of 24 hours of monitoring one of the workloads. And on the x-axis, you can see the duration of the tasks. That's basically how long it took to process a task. And on the y-axis, you can see how many times this particular task has appeared, right? There are two main insights from the graphs, from this graph. So first of all, the most of the tasks are very short. So in fact, 40% of these tasks in this particular sample have been completed in less than 2 seconds. And the second insight here is that the total number of the tasks are all very, very large. So we're talking about more than 200 million of tasks per day for this particular financial institution. Now, why this is important? The thing is, if you want to process such large volume of short-running tasks, then your scheduler also should be able to move this volume of tasks in a very efficient manner. Today, let's say a common scheduler on average can process around maybe 2,000 to 3,000 tasks per second. Now, in the contrast, the HPC grid can work at the order of 30,000 per second. Now, for these reasons, we have created HPC grid based on the requirements that we have observed. And HPC stands for high throughput computing. And as I mentioned before, it is a blueprint for building high throughput computing solutions in the cloud. So the main benefits of this solution is what financial institutions seen by using this blueprint is it's a cost saving because it removes all the third-party licensing fees, and at the same time it simplifies the infrastructure and the management of the solution. It also provides operational simplicity and reliability because a lot of this architecture is based on the fully managed services and serverless components. And as a result, we have seen speed up in adoption by customers of the solution. Now, you're welcome to go to follow this URL, and you can find all the source code and with the documentation about the solution. And now I'll give the word to Flamur.
Thank you, Kirill. Hello, everyone. So now I would say let's get into the weeds of things. We want to, learn more about how does this magic thing work. Before that, we want to look at what are the design tenets under which we actually started HPC Grid. Kirill already spoke about all of the, say, functional requirements around what would such a workload require in this case, the financial service institutions grids to be able to efficiently run. And as we said, throughput, scale, reliability, all of that good stuff. But before that, we also wanted to actually incorporate some basic design principles that we build the solution with that we actually believe are very important for the success of the project, but also equally allow it to reach the scale at which it runs. So as Kirill said, it's a cloud-native solution. So we built it as cloud-native from scratch. So by default, it uses all serverless components, managed services, and is actually on the path, hopefully, to become a cloud-agnostic blueprint for running HPC systems on the cloud. The other second thing was achieving that solution to be able to handle all of these 40% of below 2% tasks, 2-second tasks, sorry. It actually required a solution that is able to scale very high and have a high throughput. So HPC Grid, as we have tested today, it's not the limit by far. We have seen handle 30,000 tasks per second. So that's the actual throughput of the scheduler. But also equally, if you have a round trip time of say a zero-sum task, the actual from scheduling to completion minus the compute time is 0.3 seconds, 300 milliseconds. So it's a very fast system from a scheduling perspective, but it also allows you to actually run different types of tasks from end of day to intraday to potentially real-time risk as well. Another of the basic design principles of HPC is actually its modularity. So we actually wanted to build it in a plug-and-play kind of manner so that customers would be able to plug in different components depending on their requirements, as well as the services that are actually more familiar to use. And we'll look at that in the architecture slide after this. Now, the next one is an interesting one, and we usually get a lot of questions about this that people don't necessarily understand what that means, but it says that all compute is a Lambda. Now, this does not mean that it only uses AWS Lambda as a service to run this. However, AWS Lambda, when it started as the whole function as a service kind of ecosystem, has a very goodly documented API. It actually basically takes two things: the function you're going to run and the input you're giving it, and then it gives you an output. You don't necessarily need to care about how does the API work, how is it implemented. Those are the internals of the actual function that you give it. It just takes an input and gives you an output. So because of this, we actually wanted to simplify the way you run all compute that is within HPC Grid. So everything that you plug in actually implements or runs under the compute that is a Lambda API. Again, we'll look at this from an architectural perspective, but this just means that if you have 10 different QR libraries in your business, you can actually plug all of them in, and you don't have to think about how would you speak to all 10 of them differently. You just speak through the Lambda interface, and then they actually implement that stuff internally. Then you've got another couple of interesting stories which are around like the custom and on-demand divide and conquer stuff. So if you want to build like one monolithic grid, which is how we used to do it in the old days, then everybody kind of shared resources on that, and you had to like compete with other teams. You had to make sure that you're not like running over, or the other way around, you actually had to pay for that compute that it was always on. So then you actually had to ensure that you're utilizing it, even if it meant that you're running stuff that is not really useful, right? In this case, you actually don't have to do that. Obviously, part of that is because it's cloud native, so you're only paying for what you use, but also because you can deploy multiple copies of this blueprint because it's really easy to deploy and manage. Then you're actually able to like have on-demand clusters or on-demand like ecosystems of HPC Grid that different teams have and use individually without actually overstepping on each other. And then as a last point, the replatforming is something we've seen a lot of customers do. So because you're actually moving onto a cloud-native solution, then you're already solved the like operational and like scaling challenges of the underlying grid. So as a next step, then people start looking at how can I like modernize my actual QR library on like different architectures, different CPUs, different programming languages, because it's very easy to plug and play. It's very easy for you to switch. It's very easy for you to have different flavors of this without actually having to change everything in that underlying infrastructure. So if we are to look at a very simplistic view of HPC Grid, this is more or less what it looks like. If you're familiar with HPC systems, then this is fairly traditional in that sense, that there is a like a client application portion here. There is a control plane, compute, and data plane. So the client application is basically your entry point into the system. So that's what you would use to call the APIs. It's basically a REST API, so technically it doesn't even require a connection library per se, but we implemented it to make it easier for you to plug and play to your existing system. So in the graph that Kirill showed earlier, you had all of these like triggers that do like the pre-processing of data, et cetera. As part of that flow, when you actually have a job, say that is comprised of hundreds of thousands of tasks or millions of tasks, you could have that whole blob of what you want to schedule go through that connector library, and then you send it off to be calculated on the grid. Now, when that comes in, ultimately it's going to the control plane, which is fully using serverless and managed services products. So everything here is a serverless product. And that is actually a very good thing because, one, it almost like theoretically scales infinitely because they all scale individually. You don't have to provision servers. It's not static scaling. But also equally, if you're not running anything, it doesn't cost you anything. Those are all only pay-per-use. So if the system is not scaled to run, it's basically free, although it's deployed. In the other side, then we have the compute plane. And as you can see, this is that modularity aspect that I spoke to earlier. So you've got different flavors of the compute plane that you can use. And then you basically plug and play which one you want to use for a specific deployment, but also equally, say if your company is a EC2 first or EKS first or Kubernetes first kind of company, then you actually just use that one that is specific to your workload. And then the whole thing kind of closes the loop around the data plane, which is used around the submission as well as the retrieval of tasks. So I do have a kind of more complicated architecture diagram that kind of zooms in onto how things work. I don't necessarily need to go to all of the details, but as you can see here, there's multiple lambdas that do all of the status checking, that do all of the health checking of the thing. So the control plane is already taking care of making sure that your tasks run, rescheduling if they fail, scaling up the compute that is needed for this, etc. So you don't have to do anything for it. It's a fully scalable, fully resilient system out of the box. And then here on the right side, you've got an example of, for example, how would the compute plane variant of this work with EKS, with Kubernetes. And I'll just draw your attention to a tiny bit of here. So as you can see in a compute environment, say in a traditional HPC system that's called a runner, a worker, a node, whatever the terminology that you're familiar with. In that, you've got two components. You've got the agent container, which is actually used for communicating with the control plane. One thing to take note of, and this might mean something to people that are familiar with HPC, this is a pull type system. So when you schedule something, those tasks make it into a queue, and then workers pull from that queue to start. It's not a push, so the scheduler is actually not responsible for making sure that all of the workers are alive. There's other components that do this out of the box. The agent container is what's talking to the queue, to the control plane, and doing the management of the actual lifecycle. Versus the Lambda container, again, all compute is Lambda, is where all of the magic is happening. Now, this is an interesting one because, as I said earlier, when you have, say, different asset classes in your company, and say somehow they all ended up developing their own QR libraries, then having a system which works for all of them would not be easy to do, right? In such a system, you plug that in here. So the Lambda container is a combination of the Lambda API, and then that speaks down towards your QR library directly. And because of this, you're actually able to mix and match different QR libraries, different versions. You're actually able to run one system which will combine them, et cetera. So it's very easy to build a very scalable, very resilient system. And then you've got all of the traditional cube things here that actually allow you to reach the scale that we're discussing here. So we use things like HBA, we use CADA, we use metrics to actually ensure that the cluster scales up, is able to meet all the demand when the work comes in, and then scales down when there's no work needed as well. So all of this is actually out of the box there available. So while this is the architecture, what is the future of HPC Grid look like? So we work on this project on our side. It's not our main job. We just love working on this, very passionate about it, but also equally, because we now donated this to Finos, we want the contribution and the collaboration of the whole wider community. So these are some of the features that we are planning to add. Unfortunately, no time commitment. If you want to build any of those or want to help, you're welcome to. So as we said, one of the main things that we wanted out of the donation of HPC Grid to Finos is actually to make it a cloud-agnostic solution. We don't believe that building grids should be a trivial problem in 2024. This has been solved multiple times by many companies in different ways. So we wanted to actually kickstart that journey for a lot of our customers as well as the community. In that, one of the things that we have heard is that they don't want it to be specific to AWS, which is fair. So a lot of the customers actually in the financial services industry talk about going multi-cloud. I don't believe anybody has properly gone multi-cloud in that regard, but cloud agnostic, I think, is the right term, because actually you want to be able to left and shift or switch or move or what have you. There's nothing stopping you from combining as well. So as part of that, actually, one of the next things that we want to do is generalizing the APIs so that they actually support standard APIs across different implementations. And then we will introduce a provider concept so that you can plug and play different cloud providers depending on what you want to run on. Another thing is the hybrid or private cloud. So if you do want to have this actually scheduled, because ultimately, as I said, it just runs on top of EKS or Kubernetes. So if you want to have those runners run on your on-prem Kubernetes, there's nothing stopping you from doing that either. As a second thing, modularizing. So in line with that, actually just being able to create proper Terraform modules, packages, images that are standardized and versioned for all of the different providers and codes so that you can actually pick the ones that you want to run. And then additional compute and data planes. So again, if you want to plug in your on-prem or if you want to plug in a replacement for SQS, that's technically possible as well. On the scaling front, Carpenter is one of the big things that we want to add. I don't know if anybody here is familiar with Carpenter. Show of hands. There we go, enough people. So that will actually help with the scaling of the compute plane so that it can reach the scales faster, but also diversify, use different purchasing options, etc. But also, we want to scale based on the depth metrics of the queue and actually have them go directly to the classes so that the scaling is much faster. We also have management and observability. I was talking to somebody just outside, and they were like, we're looking for a front-end person. So if anybody here is a front-end person and want to build a UI for this, voluntarily raise your hand. We would love to have you. But yeah, we would like a management UI just so that we make it a bit more, give better control to user and observability. But in that regard also, we already have metrics and dashboards, but we want to centralize them and enhance them so that you can actually get a very good visibility on what's happening in the cluster. And as a last bit, cost visibility is a big thing in this world. Any people that have actually got experience with HPC systems would be familiar with the fact that you actually need to ensure that the costs of that system are kind of kept in check. Otherwise, it can be quite a lot of money normally because of the scale. So we want to actually have visibility on this so that you can do per, say, job or task level reporting on how much it costs to run a certain job, task, scale, namespace, whatever, so that you can then potentially charge back those costs to the business. So with that QR code will take you to the source code repository. Happy for you to check it out. It's a very simple end-to-end system in that regard. Because we're using managed services and serverless components, all or most of the high throughput kind of characteristics of this system come from the fact that we're using services which kind of scale infinitely. So the actual code base around the control plane is about 4,000 lines of code. That's about it. So anybody can easily read and understand what's going on. But yeah, do please check out the code base. If you have any ideas about how would you like this system to run or what should it have as the next feature, please create an issue. We would like to hear what the community thinks about it. And yeah, if you want to raise a PR feature request, a bug, you're welcome to do so. So ultimately, we just want to learn from each other, create a broader community around this, and actually make it a proper cloud-agnostic open source solution. With that, I will give you some more resources. So if you do scan that second QR code, you'll go to that. Within the repo, there is a resources MD file, which actually gives you access to a lot of this information as well. We do have a couple of blog posts that depict how does this thing work. We have a blog post that Kirill has written around the actual benchmarking of how fast the system works and how does it scale. Again, I am very passionate about the thing, obviously, but a round trip time of 0.3 seconds in scheduling, in my opinion, is crazy good. That's insane. And the 30,000 tasks per second. So imagine the tasks are actually just doing exit 0. They're not doing any calculation. But if you submit 30,000 of them, they come back as completed within 1 second. I think, again, that's an insane scale compared to what we have today. So there's the blog post that actually gives information about this. We do have a workshop that you can run by yourself on your own AWS account. You can deploy the solution. There's Terraform code. It's all there. It's basically a couple of commands, and then you have the system running, and then you can send tasks. So as part of the workshop, as well as in the repo, actually we have a proper implementation of a end-to-end system. So there's an open source project called QuantLib, which is a open source quant library. It's not your QR like code that you have in your own companies, but it does exactly pricing and everything else that you would normally do. The implementation includes that as well. So it actually does an end-to-end pricing of some, I don't know what is the price, whatever, of some options, I think. And then it actually gives you the results end-to-end as well. So you can then just use that as a starting point, swap the QR library for your own, and then see how does that work. And then there's a couple of blogs and white papers on the topic, which Alex has contributed to as well. So with that, I would like to thank you for your attention, and we will take any questions you may have.
I think the best really depends on the customer. So it's based on their experience, right? So what they're already running on-prem, what they are familiar with, and it depends on the objective of their workload, right? So for example, some workloads can be very time sensitive, right? In this case, when it comes, for example, for the data plane, it is something like Elastic Cache for Lustre. This would be the ideal. It's give like the very, very small latency. If you want to optimize toward the cost, and if you want to move a lot of data, then S3 probably the best choice in these things. If it is, if you need POSIX file system, then there is FSX for Lustre, etc. And pretty much the same logic goes for the compute plane. So EKS, the Kubernetes would be perhaps the most common choice because of interoperability and ability to run it on-prem and in other cloud providers, etc. But again, there's no like one size fits all. It depends, and it's also possible to extend this list because again, as Flamur was saying, the overall solution is amount of code is really very small. If somebody wants to have something else, it's quite possible.
So I want to firstly debunk the first part of the question. I would not say it's early days. It's actually in use in multiple banks in production as is. And this has existed for about 3-4 years. When we first created it, it was part of the AWS open source ecosystem. The reason we donated it to FinOps is to actually enhance that collaboration with the community and other CSPs so that we make a cloud agnostic thing that I keep on banging on about. Ultimately with that, one of the reasons the FSI grids in the world today run in a couple, and I'm going to say a couple of vendor products, as well as a couple of open source solutions, is because of that high throughput requirement. So the way a lot of banks have solved this because most of them, if you look at it, it's just lots of Monte Carlo. Some of these actually finish in 1 second or less, and then others take 40 minutes. The way most customers chose to deal with this problem is by what's called bucketing, which is combining all of these to run together so that they would take longer. But ultimately, provision and compute, doing a 1 second thing and then dying is very inefficient. It doesn't actually scale, right? So that's why they kind of wanted to fill that gap by doing some pre-planning before so that they end up running the same thing. Slurm has some of those issues because its tasks per second throughput is not as big. It reaches a few hundred. It can't reach the tens of thousands we're talking about. So if you were to use something like Slurm, you can. It's actually good for certain types of workloads, but it won't reach that high TPS.
So it's about 6 hours.
So I wouldn't say sweet spot in that regard because this can work either way and can handle both. The good thing about HPC Grid is that it's actually able to, for example, based on demand, figure out how much compute is needed without you having to preset. A lot of the systems that exist out there today, vendor or open source, are because historically they were made for on-prem static, and they don't have a very good scaling capability. Because this is built for the cloud, in the cloud, actually auto-scaling is one of the design tenets. So having that ability to actually scale up based on demand, but also equally handle different durations of tasks equally the same way is the sweet spot. So I wouldn't say this is catered, and like we talk about this is Finos, we talk about it in the sense of, FSI grids, but there's nothing stopping anyone from using HPC grid for any type of HPC workload. And this actually would cater to all of those use cases as well. So I think like one of the things that we kind of want the community to realize is that this type of system, minus the couple of open source options, costs loads of money to those companies on licensing fees, on scale, because you have to preset those solutions that are there today are fairly static. They don't actually make use of the cloud APIs properly, so you lose by actually using them. This is able to give you the best, like what we call price performance at all times, because it's actually scaling with demand, but also is able to run at any scale that you configure it to. So I would say like the sweet spot is everywhere, and it's free. So why would you not? It costs nothing to run while it's not doing anything.
I didn't quite understand.
So it's future plans for it to be cloud agnostic, but it's not dependent on Lambda, and that's what I kind of like want to repeat on. When we say all compute is Lambda, it does not use AWS Lambda. It just implements the Lambda API, and there's nothing AWS specific about it. Any function as code Lambda ecosystem in the world today, we invented it, okay? But it still works the same way. All of the Lambdas out there in the world, any service, any CSP, works exactly the same way. A function, an input, an output.
Whatever. So are you using any sort of heuristics there, or?
Not really. So regardless if we use, like separations, like I said, firstly, but regardless if you use Carpenter or not, the actual definition of CPU to memory ratio is a workload requirement. We have plans on making this dynamic, and actually is probably going to be quite amazing. But the workload requirements on this type of workload today are fairly static. So when you talk to any of grid systems in the world today, they will differ between asset classes, et cetera, but they will all have a requirement of, say, my QR library needs 1 CPU to 2 gigs of memory, or if it's Java, 1 to 8 or 1 to 16. So because of this, it's actually defined when you create the deployment, because also another thing that you actually have to define is what QR library am I running? Like what type of asset classes is this pricing, et cetera. So all of these things are kind of preset, and you can't, like they don't, like the separation of concerns again, like it doesn't have anything to do with you using Carpenter or not. Carpenter will just ensure that the underlying compute is efficiently like provisioned and used, but the pods will still have the same requests and limits that you define as sort of thing. Good. I have, yeah, and then.
So I have 2 questions. First one,
It would, but that would not be a setup I would recommend anybody to do, because the cross-cloud latency is not something anybody can guarantee.
Okay, yeah. So that means if I have certain vendor data, so I'll have to first migrate it to my own cloud system?
No, so the way this works, and that's part of the beauty actually, is when you submit your tasks to the system, you see there's like 2 types of arrows. Part of that is going to the control plane, another part is going to the data plane. There is a way for you to be able to, this is not a requirement, but you can split the request in such a way that the task metadata goes into the control plane, and the actual data that the tasks deal with can be stored on the data plane, so that your tasks would be able to pull that data when they're running the tasks. And that's actually kind of a good thing, because when we saw that other graph that Kirill showed, when you're doing the actual pre-processing of the data and data fetching, you normally do stuff with that data to normalize. Certain customers will choose to anonymize the trade data and just send the numbers, and then they have the information to match it back when it comes back, or they will just like do a subset of that data that's only important for that pricing. So it all depends on how you would do that, but ultimately the system allows you to.
And just to add 2 more points here, there's nothing stopping you from pre-populating the data plane with whatever data you need, static data, and also there's nothing stopping your, let's say, workers to access any additional data store that you might need, either on-prem, another cloud provider, et cetera, et cetera. So there is flexibility.
Last question, I think we're on time. Okay, thank you very much. Thank you, everyone.
Thank you.